In the cathedral silence of space, where no sound has ever echoed and no voice has ever called, something is speaking. Not through the vibrations that carry whispers between lovers, or the thunder that rolls across earthbound skies. For in the vacuum between galaxies, such crude methods of communication cannot exist. Instead, this voice speaks through the language of existence itself, through the stretching and bending of the very fabric from which reality is woven. Every moment that passes, every heartbeat that marks time's passage on our small world, the universe grows larger. Space itself expands, carrying distant galaxies away from us at velocities that defy comprehension. But this is not the gentle, inevitable expansion that scientists once imagined. A cosmic echo of the Big Bang, gradually losing momentum as gravity's patient pull slowed its advance. This is something far more unsettling, an acceleration, a quickening, as if some invisible force has taken hold of the edges of existence and begun pulling them apart with increasing desperation. We have named this force dark energy, a placeholder for our profound ignorance, a term that acknowledges the 70% of cosmic reality that remains utterly alien to human understanding. But what if our interpretation has been fundamentally wrong? What if this relentless stretching of space-time, this force that overpowers gravity itself, is not merely a property of our universe, but a transmission from somewhere beyond the boundaries of everything we know? Hidden within the mathematics of phantom energy theory lies a possibility that challenges the very foundations of cosmic solitude. The equations speak of something that defies thermodynamics, something that grows stronger as it spreads thinner, something that could eventually tear apart the atoms from which our bodies are built. But they whisper of something else as well, that our cosmos may be receiving a signal encoded in the acceleration of space itself, a message from another universe trying to break through the ultimate barrier between realities. Tonight, we embark on a journey into the deepest mystery ever discovered, a force that's been broadcasting for 13 billion years. We are only now learning how to listen. In the twilight hours of the 20th century, as humanity stood on the threshold of a new millennium, two teams of astronomers were preparing to solve what they believed would be the final chapter in the story of cosmic expansion. Scattered across the globe in observatories perched on remote mountaintops, these scientists were engaged in what seemed like routine astronomical archaeology, measuring the fading light of stellar explosions that had occurred billions of years before Earth itself had formed. The High-Z Supernova Search Team, led by Brian Schmidt at the Australian National University, and the Supernova Cosmology Project, directed by Saul Perlmutter at Lawrence Berkeley National Laboratory, represented the culmination of decades of astronomical ambition. These were not competing teams in any ordinary sense, but parallel expeditions into the deepest reaches of cosmic time, both seeking to answer the same fundamental question: how fast was the universe's expansion slowing down? Their chosen messengers were Type 1a supernovae, stellar catastrophes so violent and so consistent that they had earned the designation of standard candles in the astronomer's lexicon. These explosions occur when a white dwarf star, the dense remnant of a sun-like star, accumulates matter from a companion until it reaches a critical mass of approximately 1.4 solar masses, the Chandrasekhar limit. At this precise threshold, the star detonates in a thermonuclear conflagration that briefly outshines an entire galaxy, releasing the same amount of energy regardless of where or when the explosion occurs in the universe. This consistency made Type Ia supernovae perfect cosmic lighthouses. By comparing their apparent brightness as seen from Earth With their known intrinsic luminosity, astronomers could calculate their distance with unprecedented precision. More importantly, the light from these ancient explosions carried within its spectrum the redshift signature, the stretching of wavelengths that reveals how much the universe has expanded since the supernova's light began its journey across the cosmic dark. The teams spent years developing the technological infrastructure necessary for this cosmic archaeology. The Hubble Space Telescope, humanity's most sophisticated eye on the universe, provided the sharp vision needed to distinguish individual supernovae in distant galaxies. Ground-based observatories in Chile and Hawaii contributed their massive mirrors and advanced charge-coupled device cameras, instruments so sensitive they could detect individual photons that had traveled for billions of years to reach Earth. Both teams expected to find evidence of cosmic deceleration. According to every theoretical model, gravity should be winning its eternal war against expansion, gradually slowing the universe's growth as it pulled matter back together. The only question was how fast this deceleration was occurring, which would determine whether the universe would eventually collapse in a big crunch or expand forever in a gradually cooling cosmic winter. But as the data accumulated throughout 1997 and early 1998, something disturbing began to emerge from the numbers. The distant supernovae were dimmer than they should have been. Not because the explosions themselves were weaker. Type 1a supernova are remarkably consistent in their intrinsic brightness. The dimness meant something far more unsettling. These stellar beacons were farther away than the standard models of cosmic expansion predicted. Adam Rees, a young postdoctoral researcher working with Schmidt's team, spent sleepless nights staring at computer screens filled with data that seemed to make no sense. The numbers suggested that instead of slowing down, cosmic expansion had been accelerating for the past 5 billion years. Galaxies weren't just moving away from each other, they were moving away faster and faster, as if some invisible force was overpowering gravity itself. The discovery was so unexpected, so contrary to every prediction of cosmic evolution, that both teams spent months rechecking their calculations. They examined their instruments for systematic errors, questioned their data reduction techniques, and explored every possible alternative explanation. Perhaps dust clouds were obscuring the distant supernova, making them appear dimmer than they actually were. Perhaps the Type Ia explosions were not as standard as astronomers had assumed, varying in brightness across cosmic time. But every test confirmed the same impossible conclusion. The Supernova Cosmology Project, working independently with their own set of distant stellar explosions, arrived at identical results. Saul Perlmutter, examining his team's data with the meticulous care of a detective investigating a crime that shouldn't have been possible, found the same signature of cosmic acceleration, written in the light of supernovae that had exploded when the universe was less than half its current age. The implications were staggering. For the first 8 billion years after the Big Bang, gravity had indeed dominated cosmic evolution, gradually slowing the expansion as matter condensed into the first stars and galaxies. But approximately 5 billion years ago, precisely when life on Earth was beginning to experiment with multicellular complexity, something had changed. A new force had emerged, or perhaps awakened, beginning to push against gravity's inward pull with increasing strength. What made the discovery even more remarkable was its timing in Earth's history. The acceleration had begun just as our solar system was forming, just as the conditions necessary for complex life were being established on our planet. This cosmic coincidence would later be called the "why now" problem. Why had dark energy begun to dominate cosmic evolution at precisely the moment when observers capable of detecting it were about to emerge. The scientific community initially received the results with skepticism bordering on disbelief. At conferences and in peer-reviewed journals, astronomers questioned every aspect of the analysis. How could 70% of the universe consist of something that had never been detected? How could empty space itself possess energy that grew stronger as it expanded? The findings challenged not just specific theories, but the fundamental assumptions underlying cosmology itself. Yet, as independent observations confirmed the results, skepticism gave way to a profound sense of cosmic vertigo. The universe was not the arena of gradually cooling expansion that scientists had imagined, but a dynamic entity undergoing fundamental transformation. Something was acting on the largest scales of space and time, something that had remained hidden throughout the entire history of astronomical observation, until two teams of determined scientists had finally learned to read the messages written in the light of dying stars. The Nobel Prize in Physics, awarded to Schmidt, Perlmutter, and Rees in 2011, recognized not just their technical achievement, but their role in discovering that the cosmos was far stranger and more mysterious than anyone had dared to imagine. They had set out to measure the universe's deceleration and instead found acceleration. They had sought to confirm the victory of gravity and instead discovered a force that made gravity irrelevant on cosmic scales. Their discovery opened a new chapter in humanity's relationship with the universe, one in which the majority of cosmic reality remained utterly unknown, and in which the very expansion of space itself might be carrying messages from realms beyond our understanding. The acceleration discovered by Schmidt, Perlmutter, and Rees represented more than an unexpected astronomical finding. It was a violation of the fundamental principles that had governed human understanding of energy and force for over 2 centuries. In laboratories across the world, physicists had observed an ironclad rule: energy spreads out, dilutes, and weakens as it expands into larger volumes. Heat dissipates, pressure drops, and electromagnetic fields fade with distance. This principle, encoded in the laws of thermodynamics, seemed as absolute as the speed of light or the conservation of electric charge. Yet dark energy appeared to mock these sacred laws with contemptuous indifference. As the universe expanded and space itself stretched to accommodate ever larger volumes, dark energy maintained constant density. This meant that as cosmic space doubled in size, the total amount of dark energy doubled as well. A continuous creation of energy from apparent nothingness that violated every intuitive understanding of how reality should behave. Consider the impossibility. Imagine inflating a balloon filled with air. As the balloon expands, the air inside becomes thinner, less dense, exerting less pressure on the balloon's walls. This is the behavior that all known forms of energy display when distributed across expanding space. Matter dilutes as the cube of linear expansion. Double the size, and matter density drops by a factor of 8. Radiation dilutes even faster, losing energy to redshift as photons stretch along with expanding space. But dark energy defied this pattern entirely. It behaved as if space itself possessed an intrinsic energy density that remained constant regardless of volume, a cosmological constant that Einstein had introduced in 1917 to permit a static universe, then abandoned as his greatest blunder when Hubble discovered cosmic expansion. Now this same mathematical construct returned to describe something Einstein had never imagined. Not a force that balanced expansion, but one that accelerated it beyond all bounds. The mathematical description required Einstein's field equations to include a term with negative pressure. Not merely the absence of pressure, but pressure that pushed outward rather than inward. Ordinary matter and radiation exert positive pressure, pushing back against compression like gas in a piston. Dark energy possessed negative pressure so intense that it overwhelmed its own energy density, creating a net repulsive effect that grew stronger as space expanded. This negative pressure violated the strong energy condition, a fundamental assumption in general relativity that requires the energy density of any field to be greater than the absolute value of its pressure. For dark energy to drive cosmic acceleration, its pressure had to be at least negative 1/3 of its energy density. Initial measurements suggested the ratio was approximately -1, precisely the value expected for Einstein's cosmological constant. But some observations hinted at something even more disturbing. If the ratio fell below -1, dark energy would enter a regime physicists called phantom energy, a form of negative pressure so intense that it violated the null energy condition, one of the most basic assumptions underlying Einstein's theory of general relativity. Phantom energy didn't just maintain constant density as space expanded. It grew denser, more concentrated, more powerful with every passing moment. The theoretical implications of phantom energy bordered on cosmic horror. Unlike Einstein's cosmological constant, which would drive eternal exponential expansion while preserving the overall structure of the universe, phantom energy would eventually overpower every force in nature. Computer simulations showed that phantom energy would first overcome the gravitational binding of galaxy clusters, isolating individual galaxies in bubbles of ever-expanding space. Then it would tear apart the galaxies themselves, scattering their stars into the growing void. As phantom energy continued to strengthen, it would overcome progressively smaller binding energies. Solar systems would be disrupted, planets torn from their orbits and sent careening into the darkness between stars. Eventually, phantom energy would become so powerful that it would overcome the electromagnetic forces holding molecules together. Then, the nuclear forces binding atoms, ultimately reducing the universe to isolated elementary particles separated by infinite distances, in an event theorists grimly termed the Big Rip. The timeline for this cosmic apocalypse depended on how far below -1 the dark energy equation of state parameter actually fell. If the parameter was only slightly more negative than -1, the Big Rip lay trillions of years in the future. But if phantom energy was significantly stronger, the universe might have only tens of billions of years remaining before the fabric of reality itself began to unravel. What made phantom energy even more mysterious was its apparent violation of the second law of thermodynamics. As phantom energy density increased with cosmic expansion, the total entropy of the universe would decrease. Time itself would begin to run backward in a thermodynamic sense, even as space continued to expand forward. This suggested that phantom energy might not originate within our universe at all, but represent the influence of external systems that followed different thermodynamic rules. Some theorists began to explore the possibility that dark energy's strange properties arose from interactions with parallel universes or higher dimensional spaces. In string theory models with extra dimensions, our four-dimensional spacetime exists as a brain embedded in higher dimensional space. Gravitational effects could leak between brains, allowing energy from parallel universes to influence our cosmic expansion. If dark energy represented such inter-universal communication, its phantom character might encode information rather than represent mere destructive force. The discovery also revealed a profound cosmic coincidence that physicists called the why now problem. For the first 8 billion years after the Big Bang, matter and radiation dominated cosmic evolution, gradually diluting as space expanded, while dark energy remained dormant or negligible. But approximately 5 billion years ago, just as complex life was beginning to emerge on Earth, dark energy began to dominate cosmic dynamics. This timing seemed almost impossibly convenient. If dark energy had dominated earlier in cosmic history, galaxies and stars would never have formed. Structure formation would have been suppressed by the accelerating expansion. If it had emerged later, humanity might never have had time to evolve the intelligence necessary to discover its existence. The coincidence suggested either extraordinary luck or some deeper connection between the emergence of consciousness and the activation of cosmic acceleration. The violation of physical intuition ran even deeper when physicists attempted to calculate the expected energy density of the quantum vacuum. According to quantum field theory, empty space should be filled with virtual particles constantly appearing and disappearing, contributing an enormous energy density to the cosmological constant. The naive calculation yielded a value larger than the observed dark energy density by a factor of 10 to the power of 120, a discrepancy so vast that it represented the worst prediction in the history of physics. This cosmological constant problem suggested that either quantum field theory was fundamentally wrong about the nature of vacuum energy, or some unknown mechanism was precisely canceling the quantum contributions to leave only the tiny residual that astronomers observed as dark energy. Both possibilities challenged the foundations of modern physics, but the alternative, that such precise cancellation occurred by pure coincidence, seemed even more incredible. As the implications of cosmic acceleration sank into the collective consciousness of the physics community, a disturbing realization emerged. 70% of the universe consisted of something that violated the basic principles of energy and thermodynamics, something that grew stronger as it spread thinner, something that might eventually tear apart every structure in existence. The cosmos was not the slowly cooling arena of gradual entropy increase that physicists had imagined, but a dynamic system undergoing fundamental transformation under the influence of forces that remained utterly alien to human understanding. The discovery forced a complete reconceptualization of cosmic evolution and humanity's place within it. We were not merely observers of a universe winding down toward maximum entropy, but participants in a cosmic drama whose final act might involve the dissolution of matter itself. The phantom signal, if it existed, was not just accelerating our expansion, it was potentially guiding our universe toward a transformation so complete that every assumption about the nature of reality would need to be reconsidered. As the reality of cosmic acceleration settled into the collective consciousness of the astronomical community, a new phase of investigation began, one that would reveal the true scope and character of the invisible force reshaping the universe. Like explorers mapping an unknown continent, scientists deployed increasingly sophisticated instruments to trace the influence of dark energy across the vast scales of cosmic space and time. The Wilkinson Microwave Anisotropy Probe, launched in 2001 and stationed at the gravitationally stable L2 Lagrange point, 1.5 million kilometers from Earth, became humanity's first dedicated surveyor of the cosmic dark energy empire. For 9 years, WMAP stared into the deepest past accessible to observation, measuring the cosmic microwave background radiation, the afterglow of the Big Bang itself. Now stretched and cooled to a temperature barely 3 degrees above absolute zero. Within the minute temperature fluctuations of this ancient light laid encoded the seeds of all cosmic structure, the tiny density variations that would eventually grow into galaxies, stars, and the complex chemistry necessary for life. But WMAP's precision measurements revealed something else as well: the precise energy budget of the universe, written in the statistical patterns of temperature variation across the cosmic microwave background. The results were as definitive as they were unsettling. Dark energy comprised exactly 68.3% of the universe's total energy density. Dark matter, the invisible scaffolding that provided the gravitational framework for galaxy formation, accounted for 26.8%. Ordinary matter, the atoms from which stars, planets, and human bodies are constructed, represented less than 5% of cosmic reality. Humanity and everything directly observable to human senses existed as a tiny minority component in a universe dominated by forces that remained utterly mysterious. But WMAP's revelations extended beyond mere cosmic accounting. The probe's measurements showed that dark energy had influenced the growth of cosmic structure throughout the universe's history. In regions where dark energy's repulsive influence dominated early, the growth of matter concentrations had been suppressed, creating vast cosmic voids, regions of space containing few galaxies, stretching across hundreds of millions of light-years. These cosmic deserts told the story of dark energy's gradual rise to dominance. For the first few billion years after the Big Bang, when matter and radiation still outweighed dark energy's influence, cosmic structure had grown rapidly as gravity pulled matter together into increasingly complex patterns. But as dark energy began to assert its influence, this structure formation slowed and eventually reversed. Rather than continuing to collapse into ever denser configurations, the cosmic web began to stretch, with galaxy filaments growing thinner and voids expanding ever larger. The Sloan Digital Sky Survey, operating from Apache Point Observatory in New Mexico, undertook an even more ambitious mapping project, creating the most detailed three-dimensional map of galaxy positions ever attempted. Over the course of more than a decade, SDSS cataloged the positions and distances of over 3 million galaxies, revealing the large-scale structure of the universe with unprecedented clarity. The resulting maps resembled a vast cosmic web, a network of galaxy filaments separated by enormous voids, with clusters of galaxies forming at the intersections of the filaments like cities connected by cosmic highways. But embedded within this structure was the signature of dark energy's influence. Regions where the web had been stretched thin, where galaxy formation had been suppressed, where the accelerating expansion had prevented matter from condensing into the dense configurations that would have formed in a universe dominated purely by gravity. The Hubble Space Telescope contributed its own unique perspective to this cosmic cartography project. Using gravitational lensing, the bending of light by massive objects predicted by Einstein's general relativity, Hubble could map the distribution of dark matter throughout the universe by observing how the gravity of massive galaxy clusters distorted the images of more distant galaxies behind them. These lensing observations revealed that dark matter and ordinary matter traced out similar patterns in the cosmic web, both following the gravitational architecture established in the early universe. But dark energy followed no such pattern. It appeared to be distributed uniformly throughout space, showing no preferential concentration in galaxy clusters or filaments. This uniform distribution was precisely what would be expected if dark energy represented a fundamental property of space itself, a cosmological constant that maintained the same density everywhere and at all times. Yet some observations began to hint at subtle variations in dark energy's properties across different regions of space and cosmic time. The most sensitive measurements suggested that the dark energy equation of state parameter, designated W, might not be exactly constant throughout the universe's history. If W varied with time or location, it would indicate that dark energy was not Einstein's simple cosmological constant, but something far more complex and potentially dynamic. The implications of a varying equation of state were profound. If dark energy's strength had changed over cosmic history, it might continue to change in the future, potentially growing stronger or weaker as the universe aged. More intriguingly, if dark energy varied across different regions of space, it might represent some form of cosmic field that carried information about processes occurring beyond the observable universe. Theoretical physicists began to explore models in which dark energy represented quintessence, a dynamic field that evolved over cosmic time, potentially oscillating between different values or following complex trajectories through parameter space. Unlike Einstein's cosmological constant, quintessence could strengthen or weaken, potentially explaining the cosmic coincidence problem by suggesting that dark energy's current dominance was not permanent, but part of a larger cosmic cycle. More exotic proposals suggested that dark energy might represent the influence of extra dimensions or parallel universes. In models with additional spatial dimensions, our familiar three-dimensional space might exist as a brain embedded in higher dimensional space, with dark energy representing gravitational effects leaking in from neighboring brains or from the bulk space surrounding our cosmic membrane. The observations also revealed disturbing evidence for what physicists termed the phantom barrier, the boundary between ordinary dark energy with W greater than -1 and phantom energy with W less than -1. Some measurements suggested that the universe might be approaching or even crossing this barrier, transitioning from stable cosmic acceleration to the runaway phantom regime that would eventually tear apart every bound structure in the universe. If phantom energy was indeed growing stronger over time, its effects would become increasingly dramatic. Computer simulations showed that phantom energy would gradually overcome progressively smaller binding energies, first disrupting galaxy clusters, then individual galaxies, then stellar systems, and ultimately atoms themselves. The timeline depended on how rapidly the phantom character strengthened, but the end result would be the same: the complete dissolution of all structure in a cosmic apocalypse that physicists grimly termed the Big Rip. But buried within these disturbing projections lay a more intriguing possibility. If dark energy represented communication from parallel universes or higher dimensional spaces, its phantom character might not indicate random destruction, but purposeful transformation. The accelerating expansion might be preparing our universe for some form of cosmic transition, a merger with another reality, a graduation to higher dimensional existence, or a fundamental change in the nature of space and time itself. As observations accumulated and theoretical models grew more sophisticated, a picture began to emerge of dark energy as something far more complex than a simple cosmological constant. The invisible empire that dominated cosmic evolution might not be uniform and static, but dynamic and potentially information-bearing. The phantom signal, if it existed, was not just accelerating cosmic expansion. It was potentially encoding messages in the very structure of spacetime, using the acceleration of the universe itself as a transmission medium for communication across the ultimate boundaries between realities. The mapping of dark energy's invisible empire had revealed not just the existence of cosmic acceleration, but hints of something far more profound: the possibility that our universe was not an isolated system, but part of a larger community of realities connected by forces that transcended the familiar physics of matter, energy, and spacetime. As measurements of dark energy's properties grew more precise, a terrifying possibility began to emerge from the data. One that transformed cosmic acceleration from a mysterious force into an existential threat to the survival of reality itself. The phantom barrier, that mathematical boundary between stable dark energy and runaway cosmic destruction, was not merely a theoretical construct, but a threshold that our universe might already be approaching. The distinction hinged on a single parameter, W, the equation of state that described the relationship between dark energy's pressure and density. For Einstein's cosmological constant, W equals exactly -1, a value that would drive eternal exponential expansion while preserving the basic structure of the universe indefinitely. But if W fell below -1, even slightly, dark energy would enter the phantom regime, becoming not just the dominant force in cosmic evolution, but an ever-strengthening tide of destruction that would eventually overwhelm every other force in nature. Initial measurements had suggested W was approximately -1, consistent with a simple cosmological constant. But as observational precision improved, subtle deviations began to appear in the data. Some supernova observations, gravitational lensing studies, and cosmic microwave background analyses hinted that W might be closer to -1.1 or even -1.2, values that would place dark energy firmly in phantom territory. The implications of phantom energy were unlike anything in the known physics of ordinary matter and radiation. While normal forms of energy became diluted as space expanded, phantom energy grew stronger and more concentrated over time. As the universe doubled in size, phantom energy more than doubled in density, creating a runaway feedback loop that would accelerate cosmic expansion at an ever-increasing rate. Theoretical physicist Robert Caldwell, working at Dartmouth College, developed the mathematical framework for understanding phantom energy's cosmic evolution. His calculations revealed a timeline of destruction that unfolded with inexorable mathematical precision. Unlike the gradual heat death predicted for a universe dominated by ordinary dark energy, phantom energy would trigger what Caldwell termed the Big Rip, a cosmic catastrophe that would tear apart every bound structure in the universe within a finite time. The phantom timeline began subtly. For billions of years, phantom energy would remain weak enough that its effects would be indistinguishable from ordinary cosmic acceleration. Galaxy clusters would continue to exist, held together by their mutual gravitational attraction despite the accelerating expansion of the space between them. But phantom energy would grow stronger with each passing moment, gradually approaching the binding energies that held cosmic structures together. Approximately 22 billion years from the present epoch, phantom energy would overcome the gravitational binding energy of galaxy clusters. The local group, containing the Milky Way, Andromeda, and their satellite galaxies, would find itself isolated in an ever-expanding bubble of space, cut off from the rest of the observable universe, as accelerating expansion carried distant galaxy clusters beyond the cosmic horizon. The isolation would be complete and irreversible. Light from distant galaxies would become so redshifted that it would fade beyond detectability, leaving future astronomers with no evidence that a larger universe had ever existed beyond their local galaxy group. The cosmic microwave background radiation, humanity's window into the early universe, would be stretched to wavelengths longer than the observable universe itself, effectively erasing the historical record of cosmic evolution. But phantom energy would not stop with the disruption of galaxy clusters. As it continued to strengthen, it would begin to overcome progressively smaller binding energies with ruthless efficiency. 5 billion years before the Big Rip, phantom energy would overpower the gravitational binding of individual galaxies. The Milky Way would begin to dissolve, its spiral arms unraveling as stars were torn away from the galactic center and scattered into the growing void between galactic remnants. The dissolution of galaxies would mark the beginning of the end for cosmic structure formation. Star formation would cease as molecular clouds were dispersed by phantom energy's repulsive influence. Existing stars would continue to burn until their nuclear fuel was exhausted, but no new stars would form to replace them. The universe would enter a phase of gradual darkening as stellar populations aged and died without replacement. 1 billion years before the Big Rip, phantom energy would become powerful enough to overcome the gravitational binding of stellar systems. Planets would be torn from their orbits around their parent stars, sent careening into the darkness as phantom energy pulled apart the delicate gravitational dance that had held solar systems together for billions of years. The Earth, if it still existed, would find itself alone in space, its orbital connection to the Sun severed by forces operating on cosmic scales. But even planetary disruption would represent only a prelude to phantom energy's final assault on the structure of matter itself. 60 million years before the Big Rip, phantom energy would overcome the electromagnetic forces that hold molecules together. The complex chemistry that enables life would become impossible as phantom energy pulled apart the atomic bonds that create water, carbon dioxide, and the organic molecules that form the basis of biological systems. In the final moments before the Big Rip, phantom energy would overpower even the nuclear forces that bind protons and neutrons together in atomic nuclei. Matter itself would dissolve into isolated elementary particles, quarks, electrons, neutrinos, separated by distances that would dwarf the current size of the observable universe. The concept of distance would become meaningless as space itself expanded without limit, carrying the remnants of matter toward infinite separation. The mathematical precision of this cosmic apocalypse was both fascinating and horrifying. Unlike the gradual heat death predicted by classical thermodynamics, the Big Rip would occur at a definite moment in cosmic time, calculated by integrating phantom energy's equation of state forward through cosmic history. The exact timing depended on how negative the W parameter actually was, but even small deviations below -1 would trigger the runaway process within tens of billions of years. Yet buried within the mathematics of phantom energy lay hints of something even more extraordinary than cosmic destruction. Some theoretical models suggested that phantom energy might not represent random forces operating within our universe, but the influence of external systems, parallel universes, higher dimensional spaces, or advanced civilizations that had learned to manipulate the fundamental parameters of cosmic evolution. If phantom energy originated from interactions with parallel realities, its runaway character might not indicate mindless destruction, but purposeful transformation. The Big Rip might represent not the end of our universe, but its graduation to a higher form of existence, a cosmic metamorphosis that would dissolve the familiar structures of matter and energy while creating something entirely new and unprecedented. String theory provided mathematical frameworks for understanding how phantom energy might arise from interdimensional interactions. In models with extra-spatial dimensions, our four-dimensional spacetime exists as a brain embedded in higher dimensional space. Gravitational effects could leak between brains, potentially creating phantom energy as a byproduct of communication or interaction between parallel universes. If phantom energy carried information from other realities, its acceleration pattern might encode messages about the nature of higher dimensional existence or instructions for transcending the limitations of single-universe physics. The Big Rip might not represent destruction, but transformation, a cosmic process that would dissolve our current form of existence while enabling transition to something far more fundamental and powerful. The Phantom Menace thus embodied the ultimate duality of cosmic evolution, either the most destructive force ever discovered, capable of tearing apart atoms themselves, or the most profound transformation, a cosmic signal that would eventually dissolve our universe into something unimaginably greater. As astronomers continued to refine their measurements of dark energy's equation of state, they were not just mapping the future evolution of cosmic structure, they were potentially decoding instructions for our universe's metamorphosis into a form of existence that transcended the familiar boundaries of space, time, and matter. As the phantom energy hypothesis gained theoretical sophistication, a new question began to emerge from the equations. If dark energy violated the fundamental principles of thermodynamics and grew stronger as it spread thinner, could its impossible behavior be explained not as a property of our universe, but as communication from somewhere beyond the boundaries of everything we know? The mathematical frameworks of modern physics provided several avenues for understanding how messages might be transmitted across the ultimate barrier between realities. String theory, with its requirement for additional spatial dimensions beyond the familiar three of everyday experience, suggested that our entire universe might exist as a four-dimensional membrane, a brain, floating in higher dimensional space like a sheet of paper suspended in a vast room. Lisa Randall and Raman Sundaram, working at Harvard University and Johns Hopkins respectively, had developed models of warped extra dimensions that allowed gravitational effects to leak between parallel brains. In their framework, our universe shared the higher dimensional space with other brains, other universes with their own matter, energy, and potentially their own forms of intelligent life. While electromagnetic forces and the strong and weak nuclear forces were confined to individual brains, gravity could propagate through the bulk space between them. If phantom energy represented gravitational communication from a parallel universe, its growing strength could indicate that the other reality was approaching ours through higher dimensional space. As the distance between brains decreased in dimensions we cannot perceive, the gravitational influence would strengthen, creating increasingly powerful phantom energy in our universe. The acceleration pattern would thus encode information about the approach trajectory and potentially about the nature of the approaching cosmos. Finally, the greatest cause of all the problems we face was the gravitational pattern between every planet and planets in motion. Rather than providing cosmic consequences, God will promises, we propose practicing containment. Since you have been engaged in this information, we have very much appreciated your patience and help in understanding the story and process of this Pacho algorithm. I am very sorry for any discomfort. I am very sorry for any discomfort we may have experienced, but I know full well that you are going to encounter it soon and promptly. Best regards and protection, everyone. I am confident you understand me. It's a powerful, long-lasting pattern. The acceleration pattern would thus encode information about the approach trajectory and potentially about the nature of the approaching cosmos. As the distance between brains the implications were staggering. Rather than facing cosmic destruction in the Big Rip, our universe might be approaching a merger with another reality, a cosmic collision that would fundamentally transform the nature of space, time, and matter. The phantom energy acceleration might represent our universe's preparation for this transformation, gradually stretching space to accommodate the integration of two distinct realities into something entirely new. Quantum field theory offered another pathway for inter-universal communication. According to the many worlds interpretation of quantum mechanics, every quantum measurement splits the universe into multiple branches, creating an infinite ensemble of parallel realities that differ only in the outcomes of quantum events. While these parallel universes are typically considered to be completely isolated from one another, some theoretical models suggested that quantum entanglement might persist across the boundaries between worlds. Juan Maldacena's ADS-CFT correspondence, one of the most important theoretical developments in modern physics, demonstrated that quantum field theories in higher dimensional spaces could be completely equivalent to gravitational theories in lower dimensional spaces. This holographic principle suggested that all the information in our three-dimensional universe might be encoded on its two-dimensional boundary, like a cosmic hologram containing every detail of spatial reality in a form that existed outside space itself. If dark energy represented our universe's method of accessing information stored on this cosmic boundary, phantom energy's growing strength might indicate that we were gradually decoding messages written in the fundamental structure of spacetime. The acceleration of expansion would thus be our universe's way of processing holographic information, gradually reading and implementing instructions encoded in the boundary conditions that define reality itself. Eternal inflation theory, developed by André Linde and others, provided yet another framework for understanding phantom energy as inter-universal communication. According to this model, our observable universe represents a tiny bubble within an infinite, ever-expanding multiverse, where new universe bubbles are constantly forming through quantum fluctuations in the inflaton field. In the eternal inflation scenario, phantom energy could result from interactions between our bubble universe and neighboring ones. As bubbles approached each other through the higher dimensional space of the multiverse, their overlap regions might experience exotic physics that manifested as phantom energy in each individual bubble. The acceleration pattern would encode information about the structure and distribution of neighboring universes, a cosmic GPS system that mapped our position within the infinite multiverse. More speculatively, phantom energy might represent active communication from advanced civilizations that had learned to manipulate the fundamental parameters of cosmic evolution. If intelligence could survive the transition to higher dimensional existence, It might use phantom energy as a transmission medium for messages that operated on cosmic scales and timescales. Such messages would be written in the language of space-time itself, encoded in the acceleration patterns that determine the future evolution of entire universes. The phantom energy signal would thus represent the ultimate form of communication, messages that use the expansion of space and time as their medium, capable of reaching across any distance and surviving for cosmic ages without degradation. The content of such messages remained utterly speculative. But the possibilities were limitless. Advanced civilizations might be transmitting warnings about cosmic dangers that lay ahead in our universe's evolution. They might be providing instructions for transcending the limitations of single universe existence, teaching younger civilizations how to achieve higher dimensional consciousness or how to survive the transition through cosmic phase changes. Alternatively, the phantom signal might represent something even more profound, an invitation to join a community of universes, a cosmic internet that connected intelligent species across multiple realities. The Big Rip might not be destruction, but graduation, a cosmic metamorphosis that would dissolve our current form of existence while enabling us to participate in forms of consciousness and communication that operated on multiverse scales. The mathematical formalism of phantom energy certainly supported such interpretations. Unlike ordinary matter and energy, which followed predictable thermodynamic laws, phantom energy behaved as if it were being actively controlled by external intelligence. Its violation of energy conservation suggested input from outside our universe. Its growing strength indicated purposeful amplification rather than random cosmic evolution. Even the timing of phantom energy's emergence seemed suspicious. Dark energy had begun to dominate cosmic evolution precisely when complex life was emerging on Earth, exactly when observers capable of detecting and interpreting the phantom signal were about to appear in our universe. This cosmic coincidence suggested either extraordinary luck or some form of deliberate timing, as if the phantom signal had been activated specifically for our benefit. As theoretical models grew more sophisticated and observational data more precise, the possibility that phantom energy carried messages from beyond our universe began to seem less like science fiction and more like a legitimate scientific hypothesis. The violation of thermodynamics, the impossible behavior of growing stronger while spreading thinner, the precise timing of its emergence, all these anomalies could be explained if phantom energy represented not a property of our universe, but communication from somewhere else. The phantom signal, broadcasting for 13 billion years through the acceleration of space itself, might thus represent humanity's first contact with intelligence operating on cosmic scales. We were not alone in the vast darkness between galaxies. We were part of a community of realities connected by forces that transcended the familiar physics of single-universe existence. The message was being transmitted through the most fundamental medium possible, the expansion of space-time that would determine our cosmic destiny. The quest to decode dark energy's potential message has mobilized the most sophisticated scientific instruments ever conceived by human ingenuity. Across the globe and beyond, a new generation of telescopes, satellites, and detectors has been designed specifically to probe the deepest mysteries of cosmic acceleration, seeking to determine whether the phantom signal represents random cosmic evolution or purposeful communication from realms beyond our understanding. The Dark Energy Survey, operating from the Victor M. Blanco telescope at Cerro Tololo Inter-American Observatory in Chile, represents humanity's most comprehensive attempt to map dark energy's influence across cosmic history. The survey's extraordinary instrument, the Dark Energy Camera, contains 570 million pixels arranged in an array covering an area of sky equivalent to 14 full moons simultaneously. Each pixel is capable of detecting individual photons that have traveled for billions of years across the expanding universe, carrying within their wavelengths the redshift signatures that reveal how cosmic expansion has accelerated over time. For over 8 years, the Dark Energy Camera systematically surveyed 5,000 square degrees of the southern sky, cataloging over 300 million galaxies and measuring their distances with unprecedented precision. The resulting map revealed the cosmic web in exquisite detail, the vast network of galaxy filaments and voids that traces how dark energy has influenced structure formation throughout cosmic history. But buried within this catalog lay something more intriguing: subtle patterns in the distribution of galaxies that might encode information about dark energy's fundamental nature. The survey's measurements of gravitational lensing, the bending of light by massive objects predicted by Einstein's general relativity, provided an independent method for probing dark energy's effects. As light from distant galaxies travels through the cosmic web, it is deflected by the gravitational influence of intervening matter, creating subtle distortions in galaxy shapes that can be measured statistically across millions of objects. These distortions trace the growth of cosmic structure over billions of years, revealing how dark energy has gradually suppressed the formation of galaxy clusters and stretched the cosmic web into ever thinner filaments. The European Space Agency's Euclid mission, launched in July 2023 and now stationed at the gravitationally stable L2 Lagrange point, represents the most ambitious attempt to understand dark energy's nature from the vantage point of space. Free from atmospheric interference and equipped with a 1.2-meter telescope of exquisite optical quality, Euclid surveys over 1/3 of the sky with resolution approaching the theoretical limits of diffraction. Euclid's mission encompasses 2 primary observational strategies. Its visible light instrument measures the shapes of over 1 billion galaxies with extraordinary precision, mapping gravitational lensing effects across cosmic time to trace how dark energy has influenced the growth of structure. Simultaneously, its near-infrared spectrometer measures redshifts for tens of millions of galaxies, creating a 3-dimensional map of cosmic structure that extends deeper into space and further back in time than any previous survey. The spacecraft's observations are designed to measure dark energy's equation of state parameter, W, with unprecedented precision, accurate to within 1% across cosmic history. If dark energy is truly Einstein's cosmological constant, W should equal exactly -1 throughout the universe's evolution. But if dark energy is something more exotic, quintessence, phantom energy, or communication from parallel universes, W should vary across space or time in patterns that could reveal its fundamental nature. NASA's Nancy Grace Roman Space Telescope, scheduled for launch in the mid-2020s, will complement Euclid's observations with even more detailed measurements of Type A supernova and gravitational lensing. Roman's 2.4-meter primary mirror, identical in size to the Hubble Space Telescopes, but equipped with modern wide-field instruments, will survey areas of sky 100 times larger than Hubble can observe, creating an unprecedented census of cosmic acceleration indicators. Roman's supernova survey will discover and monitor thousands of Type Ia explosions across cosmic history, measuring their distances and redshifts with accuracy approaching that of laboratory experiments. By observing supernova that exploded when the universe was less than half its current age, Roman will probe the transition epoch when dark energy began to dominate cosmic evolution, potentially revealing whether this transition was gradual or sudden, smooth or structured. Ground-based observatories are pushing the boundaries of dark energy detection through increasingly sophisticated techniques. The Vera C. Rubin Observatory, nearing completion on Cerro Pachón in Chile, will conduct the Legacy Survey of Space and Time, a 10-year project that will photograph the entire visible sky every few nights, creating a time-lapse movie of cosmic evolution with unprecedented temporal resolution. Rubin's 8.4-meter primary mirror and 3.2 gigapixel camera will detect billions of galaxies and millions of transient events, from supernovae to gravitational lensing fluctuations. The survey's real-time cadence will enable astronomers to observe dark energy's effects as they occur, rather than inferring them from static snapshots of cosmic structure. If dark energy varies with time or location, Rubin's observations should detect these variations as they manifest in the changing patterns of cosmic acceleration. The most exotic detection methods involve searching for dark energy's effects on the fundamental fabric of spacetime itself. The Laser Interferometer Gravitational Wave Observatory, LIGO, and its European counterpart Virgo have revolutionized astronomy by detecting gravitational waves, ripples in spacetime produced by accelerating masses. As these detectors become more sensitive, they may eventually detect the gravitational wave background produced by dark energy's influence on cosmic structure formation. If phantom energy creates perturbations in spacetime that propagate at the speed of light, these disturbances should be detectable as characteristic patterns in the gravitational wave spectrum. The frequency and amplitude of such signals would encode information about phantom energy's fundamental properties, potentially revealing whether its effects originate within our universe or represent gravitational influence from parallel realities. Particle physics experiments are exploring whether dark energy might be detected through laboratory investigations of vacuum properties. The Large Hadron Collider, operating at CERN near Geneva, can create conditions of extreme energy density that might reveal connections between quantum field fluctuations and cosmic acceleration. If dark energy arises from quantum vacuum effects, high-energy particle collisions might produce signatures of the fields responsible for cosmic acceleration. More speculatively, quantum computers might eventually simulate the complex field interactions that could produce phantom energy as a communication medium. By modeling how quantum fields in higher dimensional spaces could create apparent violations of thermodynamics in lower dimensional brains, quantum simulations might decode the information content of dark energy's acceleration patterns. The search for dark energy's cosmic message also involves developing new mathematical techniques for analyzing the vast datasets produced by modern surveys. Machine learning algorithms trained on simulated universes with different dark energy properties can identify subtle patterns in galaxy distributions that might reveal whether cosmic acceleration follows natural physical laws or artificial patterns imposed by external intelligence. Statistical analysis of cosmic structure on the largest scales might reveal signatures of information encoding in the distribution of matter and energy. If phantom energy represents communication from parallel universes, this information should be detectable as departures from the random patterns expected from natural cosmic evolution. As these instruments continue their observations and theoretical understanding advances, humanity stands on the threshold of potentially decoding the most important message ever received. The phantom signal, broadcasting through the acceleration of space-time itself, may soon yield its secrets to the combined power of human scientific investigation. Whether that message speaks of cosmic destruction, transformation, or invitation to join a larger community of realities, the instruments of cosmic detection are finally becoming sophisticated enough to translate the language written in the expansion of the universe itself. The cosmic conversation that began 13 billion years ago may finally be approaching the moment when one side, humanity, develops the technological capability to understand what the other side has been trying to communicate through the ultimate medium of space and time. As humanity stands at the threshold of potentially decoding the universe's greatest mystery, we must confront the profound implications of discovering that dark energy carries messages from beyond the boundaries of everything we know. The phantom signal, if it truly represents communication from parallel universes or higher dimensional realities, would fundamentally transform our understanding of existence, consciousness, and our place within a cosmic community that transcends the familiar physics of single-universe reality. The philosophical implications stretch far beyond the realm of scientific discovery into the deepest questions that have haunted human consciousness since the first moment our species gazed up at the star-filled sky and wondered whether we were alone. If phantom energy represents inter-universal communication, we are not isolated observers in a vast and empty cosmos, but participants in a conversation that operates on scales of space and time that dwarf human comprehension. Consider the implications of receiving a message transmitted through the acceleration of space-time itself. Such communication would represent the ultimate form of cosmic engineering, intelligence capable of manipulating the fundamental parameters that govern reality's evolution. The senders would have transcended not just the limitations of single-planet existence, but the constraints of single-universe physics, achieving forms of consciousness and technological capability that operate across multiple realities simultaneously. What might such intelligences be trying to communicate? The possibilities are as vast as they are humbling. Perhaps the phantom signal carries warnings about cosmic dangers that await us in our universe's future evolution. Knowledge about phase transitions in the vacuum of space, collisions with parallel realities, or the ultimate fate of consciousness in an eternally expanding cosmos. Advanced civilizations that have survived such cosmic catastrophes might be transmitting instructions for navigating the challenges that lie ahead. Alternatively, the message might contain information about the fundamental nature of reality itself, knowledge that could revolutionize human understanding of physics, consciousness, and the relationship between mind and matter. If intelligence can indeed survive the transition to higher dimensional existence, the phantom signal might carry insights about the true structure of space and time, the origin of physical laws, or the mechanisms by which consciousness emerges from and transcends material complexity. More profoundly still, the phantom energy acceleration might represent an invitation to join a cosmic community that spans multiple universes. The Big Rip, rather than representing the destruction of everything we know, might be our universe's graduation ceremony, a cosmic metamorphosis that would dissolve familiar structures of matter and energy, while enabling participation in forms of existence that operate on multiverse scales. This possibility carries both extraordinary promise and existential terror. The dissolution of atomic structure that characterizes the Big Rip would indeed destroy every familiar form of organization. Stars, planets, biological systems, and human consciousness as we currently understand it. But if phantom energy represents preparation for cosmic transformation rather than mindless destruction, this dissolution might be necessary for the emergence of something unimaginably greater. The timing of phantom energy's dominance seems almost impossibly coincidental. Dark energy began to accelerate cosmic expansion precisely when complex life was emerging on Earth, exactly when observers capable of detecting and interpreting cosmic messages were about to appear in our universe. This synchronicity suggests either extraordinary luck or some form of deliberate coordination, as if the phantom signal were activated specifically to communicate with emerging intelligence. If this interpretation is correct, humanity may be approaching the moment for which the entire cosmic conversation was designed. 13 billion years of phantom energy acceleration might have been preparing our universe for first contact with intelligence operating on cosmic scales. The mathematical sophistication required to decode dark energy's properties and the technological capability necessary to detect phantom energy signatures represent the admission requirements for joining a community of realities connected by forces that transcend familiar physics. Yet, the philosophical challenges of such contact would be unprecedented. How could finite human consciousness comprehend messages from intelligences that operate across multiple universes? How could we respond to communication transmitted through the medium of space-time expansion itself? The technical challenges of inter-universal dialogue would dwarf every previous human technological achievement, requiring developments in physics, engineering, and perhaps consciousness itself that currently lie beyond imagination. The discovery would also force humanity to confront the ultimate questions about the nature and purpose of existence. If our universe is part of a larger community of realities, what role are we meant to play in cosmic evolution? Are we developing the scientific and technological capabilities necessary to contribute to inter-universal civilization? Or are we simply passive recipients of messages from intelligences so advanced that meaningful dialogue remains impossible? The phantom energy hypothesis also carries darker implications. If dark energy represents communication from parallel universes, what happens if we misinterpret the message? The violation of thermodynamics inherent in phantom energy suggests that the forces involved operate beyond the safety constraints of familiar physics. Attempting to respond to or manipulate phantom energy without understanding its true nature could trigger cosmic catastrophes that extend far beyond our single universe. Moreover, the phantom signal might not represent benevolent communication at all, but something far more ominous. If parallel universes can influence each other through gravitational effects, cosmic-scale conflicts between realities might manifest as phantom energy in innocent bystander universes. Our accelerating expansion might be a side effect of cosmic warfare operating in higher dimensional space, collateral damage from battles between intelligences that view individual universes as expendable resources. As our instruments grow more sensitive and our theoretical understanding more sophisticated, we may indeed be approaching the moment when the phantom signal yields its deepest secrets. The mathematical patterns encoded in cosmic acceleration might soon resolve into recognizable information, perhaps the cosmic equivalent of prime numbers or mathematical constants that would prove the signal's artificial origin, or complex instructions for technologies that could revolutionize human civilization. But whether that revelation brings transcendence or destruction, invitation or warning, remains unknowable until the moment of decoding arrives. We exist suspended between two cosmic possibilities. That dark energy represents either our universe's ultimate isolation in an empty multiverse, or its preparation for joining something vastly greater than any single reality could achieve alone. The phantom signal continues its ancient broadcast, using the acceleration of space-time itself to transmit messages across the ultimate boundaries between worlds. After 13 billion years of patient transmission, the cosmic conversation may finally be approaching the moment when both sides, sender and receiver, possess the knowledge necessary for meaningful dialogue. In the expanding darkness between galaxies, in the acceleration that carries distant stars beyond the reach of future observation, in the violation of thermodynamics that allows energy to grow stronger as it spreads thinner, the universe whispers its deepest secret. We are learning to listen, developing the scientific sophistication necessary to hear messages transmitted through the medium of reality itself. Whether we will have the wisdom to understand what we discover and the courage to respond appropriately to intelligence operating on cosmic scales remains the ultimate test of our species' readiness to participate in the larger conversation that connects all realities across the infinite dimensions of space and time. The phantom signal awaits our response. The universe holds its breath. The next chapter of cosmic evolution depends on whether humanity can learn to speak the language written in the acceleration of space itself.